Fixed. Well, uh, good evening, my theosophical buddies. This is Jeff Curtis coming to you again from the Sierra Foothills. And it's nice to have a chance to be with you again this evening. What I'm going to do tonight is continue sort of where I left off last time. And I will be illuminating some of the aspects of quantum mechanics and quantum theory that we've talked about before. I'll be bringing up some additional details. I just got the heads up that my picture's coming through from my very helpful wife. That's good to know. I'm A significant amount of this is going to be a repeat from last time, but I'm going to add a little bit and some more words and try to flesh out the idea and both include some more general ideas and some more specific ideas. So the way I titled this tonight, I think I called it In the Quantum Realm, Is There Anything Behind the Curtain? And let me explain that title a little bit before I dive any further into this. What am I getting at? What would be the quantum realm and what would be the curtain? Well, let's think about the quantum realm as the totality of reality, including aspects of it we can't see, but we can only maybe infer to greater or lesser degree. And a useful analogy here is the one about Plato's cave and the people who are in a position where they're watching shadows on the wall. They're kind of flickering, and you can see movements of people and objects playing out on the wall. What they don't know is that there's a fire in the background and people standing in front of it moving around and doing stuff. And so what's being projected to them in the direction they are able to look are these shadow figures on the wall going through some kinds of interactions and dramas and behavior. And they can observe rules, patterns, regularities in that behavior, perhaps, if they're really working hard and observant, and they're lucky enough to exist in a time where the tools of science have been developed, let's say. But they're in a really difficult position as far as understanding the full nature of the reality, which includes then the objects, the people, the living organisms, and the full drama happening in the completely three-dimensional universe right behind them that they just can't see because of the experimental situation that they're in. So quantum realm would be all of that. What you can see and measure and infer and try to learn from is the shadow images on the wall. Now, that sounds like kind of a dismal situation, but it's not hopeless. And it's sort of the situation we're in. And so keep that in mind as I further move into this and try to explain some of the current thinking, which is attempting to describe the stuff behind the curtain. In other words, the full reality that we're not looking at. So what would be a couple things that are obscured from our view by the curtain, or at least made mysterious and hard to fully appreciate? Well, two real biggies jump out in terms of things that are there behind the curtain. And one of them, the one we're going to talk about here tonight, would be the full nature of the quantum measurement problem, which I have now talked about in slightly different contexts for our last couple of meetings. And so I hope some of you have been watching these, and if not, then maybe you might want to go back and look at 2 or 3 past in order to get full context. Measurement problem, or the so-called measurement transition, is one of the very great difficult aspects of quantum theory, and it has brought about lots of lots of controversy, puzzlement, and there are many different proposed solutions, including solution from the Copenhagen originalist school of quantum theory, which is sometimes called the Bohr-Heisenberg uh, interpretation of quantum mechanics, which says just don't look behind the curtain. There's nothing useful behind the curtain. Just keep studying the heck out of those shadow images on the wall and measure everything you can measure and take every approach you can think of to understanding what is happening there with the regularities. What regularities can you see? What kinds of experiments might you construct just based on those shadow images that you're seeing up on the wall? Don't scrutinize that inscrutable stuff. You'll just get a headache and waste time and probably not get tenure. And so for a long time, that was the prevailing point of view in quantum theory. The so-called foundations of quantum theory were just work on the stuff you can measure and invent the best math you can in order to understand that and maybe predict the next experiment. Leave the details of the quantum measurement problem to posterity. Well, okay, that turned out to be very practical. One might argue that the development of quantum mechanics went faster because of the economy of effort that resulted from that, sort of narrowing the scope of the vision. But not everybody was satisfied with that. And so we've talked a couple times now about different ideas that arose, the possible role of the consciousness of the observer in helping us to solve or understand the measurement problem. Oh, another word that I use is the measurement transition. In other words, how is it that these wobbly, fuzzy, evolving in time wave function things become concrete as observed values, observed events, when we arrange our experiment in a certain way. That's called the measurement transition. So that's possibility number one. Another thing behind the curtain that we are stuck puzzling upon is the so-called Schrodinger's cat paradox. And I'm not going to go into that one tonight, but brief refresh. That's essentially addressing where's the cut, where's the line between what we know is the realm of small objects that behave according to these quantum rules and exhibit things like superposition and interference and clearly have wave-like characteristics rearing their head, even though we'd like to think we're dealing with particles, quote unquote. And there's been recent progress in one sense. So Schrodinger's paradox was he aligned a chain of events that went from a quantum particle either decaying or not, amplified up to a cat either being dead or not. And he illustrated the paradox as an expression of frustration with, well, according to the math that we know for sure, that cat can exist in a state that's 50% alive, 50% dead. Well, that's kind of offensive and ridiculous. And it points to a problem in quantum theory that is unsolved. And it's what happens to reality when you look at it. So this is related to the measurement problem, but it's a little different. Most recently, there's a report of people, I happened to read about this in New Scientist magazine, but it's all over the place right now. Fairly recent report of people being able to put small little glass beads into superposition with each other. So these are glass beads that's made of billions of silicon and oxygen atoms, and they were able to show that the rules of quantum mechanics are necessary to explain at least some of the behavior they could observe. So that's sort of a new record. Up until then, it was only buckyballs, kind of a large molecule with like 60 carbon atoms in it, and things somewhat bigger than that, up to, I think, small proteins, had been able to be put into states of superposition. In other words, 50-50 mixes of possible quantum states, which would then collapse upon being perturbed. Well, now we've got glass beads, and these are glass beads, any single one of which would be visible by a light microscope. You know, if you had a good enough microscope, you'd be able to see this thing with your eye. But under certain circumstances, yeah, quantum mechanics applies. So that's really interesting. We're marching up the chain to more and more macro type objects. That's something to keep one's eye upon, and maybe I'll have more news stories about that in the future. We'll see. Well, before I go any further into this measurement problem thing, I want to do a little brief reiteration on how modern science works, or at least in the physical sciences and physics, or physical chemistry in particular. What is this science? What is it? First off, we say the word science as though it's a noun, because it has that connotation, but it's more usefully looked upon as a verb, you know, the act of doing science. Science is a procedure. It's a set of rules and with an optimistic face towards this will work eventually, even if you're really confused right now. Set of steps. I want to just go through them. What would that be? Well, doing science would mean you observe the behavior inherent in nature. You look for patterns. You see some phenomenon that you're curious about. What's going on there? Why does this cause seem to precede that effect? And there's some reproducibility, and I can even maybe observe some patterns in the behavior. So recognizing events, patterns, behavior that you would like to know more about, perhaps in order to gain some degree of mastery and prediction ability. Well, observation, step one. Step two, very important, is come up with some kind of a guess as to what you think's going on. What is happening here? Well, maybe there's this happening. You know, there's blood flowing around inside that animal, and so if it gets injured, that seems to come out somewhere, and more in some places than other places. Yeah, you're making a guess, maybe an informed guess as to what's going on. This is also called forming a hypothesis, and that's a really good word to know and to use. The word hypothesis as substitution for guess is it would be better for us all if that were more common usage in English. Unfortunately, in common use in English, people use the word theory instead of guess or hypothesis, and that causes problems. And scientists don't do that because there's an important distinction in the lingo. You'll hear this as I keep going. So, next step, if you can, in association with your guess as to what's going on, create a mathematical model where you assign variables to certain observable things about this natural system that you're working with, and then you hypothesize, or perhaps even more formally postulate, mathematical relationships between these variables. And you think, well, okay, this plus this seems to add up to something else, which I think I can turn this problem into symbolic variables and then mathematical operations and come up with an expression that will capture at least some of this observed reality. So this is not easy. There's many more failures than successes right here. It takes a lot of determination and insight in order to do it. And sometimes you need way more than one guess. You might need a set of interlinking postulates. for mathematical statements that you think, if these mathematical statements are true in aggregate, then I think I can capture and explain some of this observed behavior. That's very difficult. It's born of much experience to be able to do it. Okay. Then what you do is you look at your equations, you turn the crank, and try to use that mathematical structure you've created, the agreed upon symbolic variables for properties in your system, to predict how Mother Nature is going to behave in a new situation, an experiment that you're going to arrange, conduct, then record the data, come up with new values of variables at the end of what you did, and then go through that in great detail and look for places where it agrees or disagrees between the prediction and the observation. And so this also is very tricky. There's many ways it can go wrong because bias can creep in. You'll see some things a little more easily than you'll see other things in your data because you're hoping your guess was right, and you find ways to discount the things in your data telling you your guess was wrong. It's hard. It's human. It's wobbly. It's messy. It doesn't work a lot of the time. Well, if you get predictions, and at least some of it works, you can then refine the math, and you can then iterate, and you go around in a circle where you're refining the math. You're also maybe learning how to do the measurements better, how to make your observations more pure and telling of what's happening, isolate variables. The whole thing gets better and better until eventually, if your mathematical structure seems to reproducibly work for at least some significant fraction of observed phenomena, then we call it a theory. It's not called a theory before that in science. That initial first wild guess is a guess or a hypothesis. That's as far as you go with it. Be alert for that. It's kind of important in terms of understanding a lot of things you'll hear just in the basic news and basic conversation. People like to use the word theory because it sounds better than wild guess, yeah? But in a lot of the time it's not. Okay, so over the period of time from about 1905 to 1930, this process rolled forward, being applied to the behavior of elementary particles, because people had sort of recently learned how to manipulate them, and technology advanced to the point where refined observations could be made, and the quantum theory of matter was born, and we ended up with a very rich mathematical structure. In order to, that structure did rest upon a set of postulates, and depending on what book you read, there's between 7 and 10 of these fundamental postulates of quantum mechanics, statements that have to be true and hang together in order for the quantum theory to work. Going through that, quantum theory arose, and we're able to refine our language and explain some big things. So one thing that we could observe, this would be relevant to the measurement transition. I'm going to show you a graph or a figure, sort of like what you've looked at before, would be this phenomenon. So diffraction. So what we have here on the left is a gun of some type. It shoots out electrons or photons or other quantum particles, and those quantum particles proceed down some apparatus, and they've been arranged in such a way that all their momentum is going in one direction. They have very little momentum in other directions. It's this collimated beam of stuff. And we left that impinge upon a target, which I'm going to represent there just as a slit, a single slit. Well, what happens is that this wave packet it spreads out in space in a way that, even though all their momentum was going in say, the x direction to begin with, when they came out of our gun, the particles acquire momentum in the z direction. Let's take z direction as being up and down, the vertical direction. And so that's a result of something called the Heisenberg uncertainty principle, HUP. And I've described this a few times before. So the mathematical statement I have there is delta z, which means the spread of the wave function in the z direction, times delta p sub z, which would be the momentum in the z direction, the spread of it, is going to be greater than or equal to h bar over 2. H bar is the Planck's constant I've talked about a few times. And that's an inverse relationship. And so what you see here in this picture is an example of an inverse relationship at work, because the slit restricts or squeezes the wave function of our particle in the z direction. So we're constricting it to go through this little narrow region of space. By virtue of the Heisenberg uncertainty principle, that necessarily creates a larger uncertainty or spread in the particle's momentum along the z direction. So we go from a very constricted z momentum to a kick, both above and below. And we then see that the trajectories of our particle spreads out. Furthermore, it has these this structure to it. You can see the lumps in probability distribution. So there's places where it's maximal and then minimal. It's kind of a wave envelope of distributions. That is predictable based upon the mathematics of wave function. Now, I will say that in order to make that work, the mathematics involves a symbolic representation for the particle that we're going to call a wave function that has an imaginary component. In other words, it has the square root of -1 in it. You're never going to touch the square root of -1. We call it imaginary for a reason. It doesn't exist per se in our everyday reality, yet we need it in order for the mathematical structure of our quantum theory to work. I hope that sounds a little bit like the difference between what we can see and the shadow play on the wall and what's really there in the larger multidimensional quantum realm that we can't directly think about because our brains aren't built that way. It's showing up. So that imaginary number, square root of -1, which we need to use it as a coefficient or a multiplier in the mathematical form of wave functions in order to get correct predictions. So that's part of what I am getting at in terms of what's behind the curtain. Well, that's a place where quantum mechanics and its logical mathematical development has very much revealed to us something behind the curtain that we can't see easily or at all, really, with our biological eyes and brains. It takes a leap of imagination and a lot of mathematical trial and error to come up with a structure which, when you turn the crank at the end, spits out correctly that observed pattern of bumps there. So, score 1 for inferring strange stuff behind the curtain that wouldn't necessarily be easy to think about otherwise. There's another mystery here, or another element, which is if you think of the physical reality of that measurement situation, where you think about the detector, that's a set of pixels. So in modern day use, that's a bunch of little charge-coupled devices, many little electronic detectors, which either get hit or not. And this experiment works in the one at a time limit. In other words, You can send these particles one at a time, and that's the best way to do it in terms of really understanding what's happening, and you still get that distribution. Why does the particle go to one of them or the other in a given run of the experiment? What's happening to cause the selection process? How does the spread out wave function of undifferentiated possibilities collapse into a singular observed result in each experimental run? Well, that's part of the measurement conundrum or problem. I'm going to show you a little bit more of the mathematical structures that come out, and this will be familiar because we already talked about this last time. In a more general sense, if we think about the mathematics of quantum theory that evolved, we came up with something called the Schrödinger equation, where we have a mathematical operator in the form of h bar, which operates on this mathematical entity psi, and that will give us, when we do the integration, a spectrum of allowed values. We call those eigenvalues, and that can be energy or position or angular momentum or any of a number of observable quantities, times the wave function back again. That's one of the crucial results of turning the crank and using the postulates. That equation works in a broad number of contexts and gives you the correct spectrum of expectation values or energies. So H operating on psi gives us a ladder of possible values of something. Let's call it the energy. A, B, C, D can be much larger, can have hundreds of possible eigenvalues there, depending on the experiment and how well you do it. But when you run the experiment, you're only ever going to see one. In this case, we see an experiment that gave us eigenvalue letter B. So the system ended up with B amount of energy, let's say. That's another embodiment of this collapse from undifferentiated many possibilities with predictable high and low probabilities into a singular one. And that, again, is what we can call the measurement problem, which is obscured from us as being behind a curtain somehow. Well, the next thing I wanted to present or mention would be that if you look back at the talks we've done before, I went through a few possible interpretations of quantum theory and the nature of this measurement problem and all the different ways people have gone after it. All the way from don't think about it, there's nothing worth scrutinizing behind the curtain, to people who are willing to get very explicit and hopefully expect that there's something there. Quantum mechanics is trying to tell us something. It's up to us to be clever enough to figure out the mathematics. What else can we add to the wave function, or what other assumptions and interactions are taking place between wave functions for different parts of our system as it merges into and becomes a single system of particle being measured by some apparatus. There's the interpretation that involves observer or conscious observer seeing something happen, so that really it all involves an elementary particle connected through an apparatus to our brain, and something registers there, and that's how reality works. And actually still doesn't really explain why one of those eigenvalues got picked, does it? There's a many worlds interpretation, which is, well, you only see one eigenvalue because you're in the universe where that's the one that happened. But all of them happened. And what you did by conducting that experiment was create many worlds. And there's a world for eigenvalue A and a world for eigenvalue B. That's the one you're in. A world for eigenvalue C. You're not in that one. And D, E. D. Okay. So that is that's popular. There are people who adhere to that theory. They find it to be the most elegant. That does away with the measurement transition. There is no transition. There's somehow a transition of you now being attached to universe with eigenvalue B having occurred. And you split off from the version of yourself in all those other universes where A, C, D, E happened. Okay. That turns out to be mathematically fairly robust. There are arguments that people bring against it. It has its appeal and its adherence. Somehow it just scares the hell out of me. I just don't know what that means. It seems just a bit much. And something we do know from our transactions in the world, experiments we do, at least in classical physics, there's an important rule called conservation of energy. And experiments don't violate conservation of energy. Well, at least non-exotic situations don't. And well, that's a heck of a lot of unconserved energy. If you doing that little experiment over here, making a particle run through a slit and then it splats out in one of a few different places on a screen, or you're measuring the energy of some molecular quantum system to figure out what energy is it in, and you find that it's in one of those particular quantum states corresponding to A, B, C, or D. That seems like a pretty simple thing to do in order to multiply universes. Think about how much energy is in a universe. That's a lot of energy to create by doing that little quantum mechanical experiment in your lab. There's an extravagance to that. So the conservation of energy objection, I think, is quite valid. One, I'm not saying don't enjoy science fiction movies like Everything Everywhere All at Once that explore the many worlds interpretation, the many worlds interpretation of quantum mechanics, especially when it's joined up with cosmology, is a lovely playground, and I'm all for it as recreation and philosophical speculation and bantering. But in terms of an actual explanation, it's not my favorite. I'm willing to turn to other ones, even though they may still be in their formative stages and coming along. I think that's a useful process. And so in our last time together, I brought up this situation, something called quantum quenching experiment, where let's say we have a molecule we're going to call an emitter. That's the E with an asterisk in the top of this figure. Suppose that's a molecule, like a phosphorescent organic molecule, let's say, in an excited state, and it's surrounded by a bunch of absorbing species that can just be the same molecule in their ground state, or it can be other different molecules in their ground states which are capable of absorbing the energy. Well, what happens over time is you find that that little packet of energy migrates. A photon, let's say, gets emitted, and it then gets absorbed by species A there, it's lower left of E in that lower panel. That's a particularly easy to think about physical embodiment relevant to, or leading to, the notion of the transactional interpretation of quantum mechanics, which you've heard me now sneaking up on incrementally, talk by talk, for the better part of a year. And it's quite appealing. I find it to be, it's very interesting, even though I'm still wrapping my head around it. in this particular book by Ruth Kastner is a great explication of this, although she's got other books that are sort of easier to read for non-specialists. If you wanted to go deeper into this particular aspect of modern science just as something to do when you have a spare couple of years, no, actually you could, a couple of months would be fine to make it through one of her more popular books and learn a lot and come out the other end richer. It would be worth doing because it's one of the ones at the bleeding edge of interpretations of quantum mechanics. And so what does that look like? What are some elements of this particular interpretation? Well, she would say that there is a non-empirical reality, we'll put it in the quantum realm, in which possible outcomes exist and actually exert an influence on the reality we're in. And so it's opening up a little bit the notion of the word real from just that which we can touch and kick here in this reality that's all the way concrete, and thinking about possibilities of wave functions and expanding and generalizing our sense of time and how time works at the quantum level at least, in terms of defining transactions. And so one more picture for tonight. What the transactional theory of quantum mechanics postulates, this is an add-on to the math. And then what people do is they take what that math says and try to come up with new experiments that can be done in order to say yes or no, or at least no, to what you're proposing. Well, here's what's being proposed in the transactional interpretation. Let's take this top panel first. So we have our emitting molecule there in the middle. And what I'm drawing is that emitter, what if it's in communication somehow with the field of absorbers all around it? And it's sending out forward in time something we're going to call offer waves. So this is an offer of transaction that goes forward in time from emitter towards absorber, and then coming back from the absorbers, well, actually simultaneously from the absorbers, coming backwards in time, is coming a counter wave. And once in a while, conditions are correct so that when the offer wave going out from the emitter and it's called a confirmation wave coming back from the absorber. I think I may have just said counter wave before. I meant to say confirmation wave. The confirmation wave coming back from the absorber, certain conditions can be met which will result in an actualized transaction. And so that situation is depicted here in the bottom figure. And so by the solid arrow proceeding from emitter to absorber, the solid line, that's an offer wave going forward in time. The dotted line is coming back from the absorber backwards in time. Can we postulate a set of conditions such that that interaction is optimized, and then somehow that particular absorber, A, wins the competition? It's the one that gets the photon or the packet of energy or the whatever it is that we're watching in this experiment. We could use the context of the electron that came through the gun that went through the slit and now spreads out in a pattern amongst possible different absorbing pixels on the film plane of our CCD detection device. That's equally valid way to think about this. Well, what we'll get into next time is some more details. And at this very moment, I could not even really explain it crisply. I mean, as much as I thought about this and read that book, I need to go into this one notch deeper in order to be able to crisply state for you what are the conditions that allow for the actualized transaction to occur. And so I'll be doing that between now and our next meeting. And also what we'll be discussing is the role of actualized transactions in establishing this thing we call space and time. What is space-time? Obviously, that's a very live conversation in physics. Well, it's the container which is defined by actualized quantum transactions is one possible answer. And so this is a case where efforts to extend quantum theory and refine and extend the mathematical apparatus that we have at our disposal also has bearing on elements of general relativity and the nature of space and time. And this is one of the very living interfaces in modern science, is the interplay between relativity, space-time, and quantum interactions, and how does the one inform the other. So that will do it for tonight. And I hope you'll all be looking forward to a bunch of ornate mathematical gibberish. I'll try to stay away from that and make it as clean as I can next time we get together. So thank you very much, and I'll see you all in a couple months. Okay, bye-bye.